Okay, hi. So now we've covered waves and their properties in quite a lot of detail. We're going to have a look at specific examples of the electromagnetic spectrum. Now, the reason it's known as a spectrum is because we have a situation going on which is something like this. So if we were to draw the waves, the electromagnetic spectrum is one continuous spectrum. You can see from left to right that it is just a case of the waves getting closer and closer and closer together. And that means that they differ in their wavelength. So they have different wavelengths. Okay, and this is directly related to the amount of energy. So your amount of energy. Okay, and the lower the wavelength means a higher amount of energy. So the further you go down this end of the spectrum, the more energy you get. Okay, and so the different types of waves, I have touched upon them before. We have radio, which has the longest wavelength, and then the wavelengths go down to microwaves. So microwaves. You then have infrared, which we've of course spoke about before as well. Then we move on to visible light. Of course, very important. That's how we see things. You then have UV, which is ultraviolet. Okay. You then have your X-rays. And lastly, you have gamma. Okay, sometimes you'll see gamma written like that. But you have gamma radiation or gamma rays. Okay, so gamma has the most energy because it has the smallest wavelength. The wavelength can go down to the level of a million times smaller than a centimeter. So they really can get quite small. Whereas radio waves could have a wavelength as long as up to 10 kilometers. So you can see there is a massive difference in the wavelengths. Okay, now you'll remember from previous videos that we mentioned that all members of the electromagnetic spectrum, so all of these different types of waves, have exactly the same speed. So they have the same speed, and in a vacuum this is 300 million meters per second. So 300 million meters per second. You could call this 300,000 kilometers per second, because this is the same thing. Or sometimes you'll see it written in standard form, which is 3 times 10 to the 8 meters per second. All three of these way of writing it are exactly the same. We're just using either different units or we're using a different form. Now this is handy because as they all have the same speed, we can use this equation. See if you can remember that the speed of a wave is equal to its frequency multiplied by its wavelength. Okay, and this means that we can always fill in for the speed. So we can always say that 300 million is equal to the frequency multiplied by the wavelength. Now what's very important here is we need to make sure that the units match. So because this is meters per second, okay, frequency will be in hertz, and wavelength must be in meters because we have meters per second, so we need meters. If we were to write down the speed of these waves in kilometers per second or whatever, we'd have to write the wavelength in kilometers, okay? Just need to make sure that those units match. Now, so let's do a quick example. Okay, so I'm going to say, work out the wavelength, so work out lambda or the wavelength of a wave with frequency of 150 million hertz. Okay, we're assuming this is an electromagnetic wave, so we're going to use the equation above. So pause the video now and have a quick go. Okay, so I hope you had a go. What we're going to do is just fill in the numbers. So what we've got is we've got 300 million. 300 million is equal to 150 million. Okay, I could have just used the word million here because they're both millions, but this is the easiest way to do it, or the most correct way to do it, multiplied by the wavelength. Okay, Now, to get the wavelength on its own, we're going to have to divide both sides by 150 million. Okay, so we need to divide both sides by 150 million, like so. And what we're going to get is, of course, this 150 million cancels out this 150 million, leaving us just the wavelength on the right-hand side. Now, 300 million divided by 150 million, that's just the same as 300 divided by 150, because we could cancel these zeros out with each other. Or it's the same as 30 divided by 15. Now 30 divided by 15 is 2, and so our wavelength is actually 2 meters, because all of this was done in meters per second and the wavelength was in meters. Okay, so our answer is 2. Okay, so very well done if you got that. There's obviously more questions that you could do, but in this video I just wanted to go over the basics of that. So I hope that helped. If you do have any questions on what we covered here, then please do send me an email directly using the link below, or comment in the box and I'll be sure to get back to you. But make sure you remember that the energy of a wavelength is related to its wavelength. So the low wavelength equals high energy, okay? So I'm just going to write that actually. So low wavelength equals high energy. As a result of that, high frequency also means high energy. Frequency equals high energy. Okay, so that's why gamma rays have the most amount of energy, because they've got the smallest wavelength and the highest frequency. Okay, so I hope that helped, and I look forward to seeing you in the next video.